So I'm going to be talking about machine learning on source code, which is something that until a month ago didn't even have a hashtag. So it's a pretty new thing. It has a new name, but there's actually lots of people that have been doing very similar things. So the goal of the talk is to tell you why we're doing machine learning on top of source code, what we're trying to do eventually, what is our roadmap, but also especially talk a little bit about how we do it. What are the techniques that we're using? We use a lot of techniques from different fields in machine learning. We didn't invent much. We're just basically trying to put pieces together and see how they work. And I'm going to try to do as many demos as possible. So if you've ever seen a talk with demos that are live, you'll see they fail. So if they fail, that's your expectation. I'm meeting them. And if they work, expectations exceeded. And at the end, the what, which is your questions. I'll ask you to keep the questions all to the end because there's actually a lot of content and I don't think we'll have enough time to cover all the things. So if we start with questions, we'll never finish. So if you've ever seen me on stage, before I always talk about Go because I used to work at Google, which I don't anymore. And since November, I used to be a developer advocate working for Google Cloud Platform doing machine learning and Go completely separately, never merging them. And now I am a VP of Developer Relations at Sourced, small startup based in Madrid, except for me, and only employee in the United States, San Francisco. And we are basically trying to figure out what it would look like if we applied machine learning, maybe find some way of actually finding AIs that are able to help programmers do their job. The slides are online, and this is a QR code, which used to be fancy some time ago. Nowadays, I think it's still the best way for people to see slides. So if you want to take a picture of that, the slides are online. You can follow up with them. Otherwise, I'll also tweet them later on. And my Twitter is Francesc, which is at the end too. OK, so let's talk about why. Why are we even doing this? The reason is very easy. Machine learning and blockchain are the words that give you money for startups. So that's why we're doing it. Actually, not only. It is a good reason for sure, but not only. Basically, what we've seen is that deep learning specifically has revolutionized a lot of different things that we thought were basically impossible to do, right? If you think about computer vision, it was basically impossible to imagine a computer understanding an image, and nowadays you can build something quite easily that will tell you exactly what kind of dog, what breed of dog you have in a picture, much better than me. Right? So this incredible advancement is really, really good. Same for natural language processing. If I say Siri or OK Google or Alexa, trying to wake up as many devices as possible, you'll be able to have a conversation with a device that not only understands you, but it actually talks back in a way that you are able to understand quite easily. And it's pretty natural most of the time, right? This is literally science fiction not that long ago. So it's an incredible advancement because of neural networks and deep learning. Then there's also Go, not the language, but the game. When we were able to beat Kasparov with chess, which was in the 90s, I think, they said, well, we still have like at least 100 years until we were able to beat anyone at Go. That was not 100 years. And not only were we able to beat everyone at Go, but we were able to beat them every single time. Every single person. So that's pretty impressive. And for me, the most important thing is, sure, machine learning is super powerful. It allows you to have self-driving cars that look super cute. That is the most adorable self-driving car you could imagine. But for me, the most important thing for this is not the fact that it was like, oh, it's cute and it's kind of fancy. It's the fact that one of the first tests that they did with, actually not one of the first, but one of the initial tests they did with these self-driving cars was to get blind people to drive them and allowing people that otherwise wouldn't be able to perform a task to actually be able to do it, gaining autonomy, right? Now, if we apply that to code, the idea is that we want to do similar things. We want automated code review. We want to be able to translate things from source code to natural language, which is kind of easy. Basically, you give some source code, and it will say, this sorts numbers. Sure, that is actually not that hard to do. A little bit harder, we want to translate from programming languages to programming languages. I have written this in Go. How do you write it in Python? A little bit harder, actually. And one day, I would like to do it the other way around. It's like, hey, write a function that sorts numbers, and it will write itself. That is actually incredibly hard, and some people might say it's impossible. I do not think it's impossible. I think that if we're able to figure out a way of having a conversation, not just giving all the information all of a sudden, but actually giving a conversation, having a conversation on which you're actually interacting with the computer and the computer is filling up the gaps of the specification you're trying to design, I think it's something we could indeed do. But it is actually the future. And as before, the goal is not to say, hey, look, we're able to do fancy things. The goal is to have more people being able to program. In this picture, I imagine that the one on the left is reviewing the code of the one on the right, right? Having someone that is able to review your code is amazing. Not everybody can do that, right? And if you have an open source project, say Go, which I know quite well, you don't want the best engineers spending most of their time reviewing code. You want them writing code. So there's a problem. It doesn't really scale and causes problems, right? So that's the kind of thing we want to help. It doesn't necessarily need that the automated code review should be 100% automated. It means that it'd be nice if I get a PR that has 1,000 lines, it actually tells me, you know, these 1,000 lines, pretty boring, basic code, but this piece of code requires your attention. And that is actually not that hard to do. And we're working on that. There's many crazy ideas later on, but we think that that is something we can achieve. So, how? Well, first we need to understand what is source code. If I ask you what is source code, how do you represent this? What would you say? Any ideas? How do you store this? As bytes, right? So you could say, this is source code. I'm gonna train a neural network giving this. And that is correct. Like every programming language I know stores bytes. But also you could say, these are the tokens, right? There's a slightly higher level of abstraction. And this is also correct. Programming languages, all of them have tokens. Actually, not all of them. There's some of them really weird that do not use tokens. They use colors and stuff like that. Let's ignore those for now. But most of them will have some kind of token, and those tokens have some type and literal values and stuff like that. You could learn from this. But also you could say, actually, when I think about a program, I do not think about the bytes nor the words. I think about the trees. I think about an abstract syntax tree, right? So we could think, I want to feed those abstract syntax trees to my neural network, which is an interesting problem. All of a sudden, you're going to have learning from structural data and graphs, which is a completely different beast. And we'll talk about that a little bit at the end. But this is basically what we're trying to work more nowadays. So let's talk about something that is also very important, which is data sets. Machine learning is, after all, just a series of data sets thrown to an algorithm and trying to distill some information out of it, right? So what do we do at Source for data sets? We have 3 different projects. I didn't say this, but everything we do at Source is completely open source, mostly Apache v2, so you can do whatever you want with it. And everything is under github.com/src-d. So we have rovers, Borges, and Siva. Rovers are simply crawlers that are around the internet trying to figure out, is this a Git repo? If it is a Git repo, I'm going to send it to Borges. Borges is a Spanish author that was also a librarian, and what it's doing is just bookkeeping. So it's basically getting all of those URLs and downloading them. And by downloading them, it's not only downloading them, but also creating root repositories, and explain what that is in the next slide in a minute. And finally, we store them not as zips or tars, but as Siva. Siva file is a format that we created specifically because we wanted something where you could append more information, still be very compact, and have constant access to any part on the file. So we created something new because we didn't have any solution for that, and it's also open source. It's also interesting to know that in Spanish, V and B sound the same, so that's why seekable indexed block, we translated to Siva, because it sounds exactly the same. What is a rooted repository? A root repository is almost like a unified a unification of all of the forks of a repo. You have forks everywhere. Forks are actually something that basically GitHub created. So GitHub actually has an API to know, is this repository a fork from something else? The problem is that most of the time, that is not really useful, because very often what people do is they do git pull and they get the git push somewhere else, maybe not even on GitHub. So what we do to identify what is actually a fork is to find the common commit identifiers, the hashes, and if we find that they actually match some subtree, then we can say, well, these were the same repo and at some point they diverged. And we're storing those only once to have smaller data sets. We published a paper, it's called Public Git Archive, and not only published the paper, but also a blog post and also the data set. So if you go to GitHub, you can download 3 terabytes of source code, which is big. So do not do it here today because the Wi-Fi is good, but you know, there's limits. The most important thing about this is that we're trying to give it to everyone. Why do we do this? Well, for computer vision, the fact that ImageNet was a network and a competition that's created for everyone, basically saying, hey, there's a challenge. Play with this, try to improve it, actually gave a lot of motivation for researchers to write new papers, saying, hey, I increased the accuracy by like 1%, and that was a paper. We're trying to figure out we're calling it CodeNet or deep code, we're not really sure, but we're trying to figure out what that would be for code. Okay, so now we have the source code, now we want to learn from it. When we're learning from code, we're learning from sequences or trees. Let's talk about sequences first. Who else has done this? Actually, many people, right? You have speech recognition. You're transforming a sequence of audio samples into a sequence of characters describing what was said during that audio clip. Sentiment analysis transforms a sequence of words or characters into positive or negative. Machine translation, for instance, will transform a sequence, hello everyone in English, to Catalan, which I'm from Barcelona, hola tothom, this is exactly the same thing, different language, that's also sequences. And finally, video recognition, which is more complicated, still a sequence of frames to a sequence of words describing what happened in the video. How is this done? Well, let's start with characters. You could try to use neural networks. How many of you have used neural networks? I'm assuming that most of you, since this is a machine learning track. Okay, so if you try to do neural networks, traditional neural networks, with a sentence, the problem is, well, how many inputs do you need, right? How many letters do you accept? And there's ways of figuring this out. Like you could say, I'm always going to accept 20 letters. And if there's less than that, I'm going to pad with spaces. And if there's more than that, I'm going to split them or whatever. But there's actually a better solution, which is using recurrent neural networks. And when you're using recurrent neural networks, basically what you do is you have one single piece of neural network that you are giving an input, getting the output, and passing it as an input again. So I'm going to say, for instance, oh, and I have Martin Gorner, which is an old coworker, gave a really good talk, TensorFlow with a PhD, which is amazing. And he has this, which kind of explains what it is quite easily, because it's not only that there's many pieces, but all of those pieces are exactly the same. And they're communicating through the output goes to the input. And also there's a section which is basically the memory that allows the neural network to remember things about what it's seen previously. And I will not get into the details of how it works, nor the mathematics, nor LSTM, nothing like that, but definitely interesting. So what we're trying to do is, I want to create a neural network that I'm going to say, listen, I've seen P-A-C-K-A-G. What is the next letter? And it's going to say something like, there's 80% that it's E because it's package, or maybe it's I because maybe it's packaging, or maybe it's something else because my English knowledge is limited. Probably there's other words that start with that. The way we're going to do this is give the first letter, get the output, and say, is this correct? Well, no. Then we're going to do backwards propagation and retrain the neural network until we get, basically, for every single letter that we're giving, it's more and more accurate to what we expect to have. So that's basically like backwards propagation, gradient descent, neural networks, basic stuff. So with that, more information about that, what would happen if we do this with all of Shakespeare works? And I don't know if you've seen this demo, but I think it's kind of cool. So train.log. So in this demo, in this program, what I did is I loaded all of the things that William Shakespeare wrote, which is apparently a lot. And I started saying, okay, these are my sequences that I'm going to be giving you. What am I predicting? Nothing, because the neural network has not been trained. So just saying 0 for everything, no character. I have no idea what the result is. Now, after training with a bunch of data sets, it's like, okay, write some Shakespeare. And it generates this, which I'm not expert, but I don't think it's Shakespeare exactly. So, okay, no problem. We're going to continue training more, right? So after this, we continue training, and still it's not giving any results. Now it starts to give some results. We just keep training. Now it's seeing 150 out of 860 patches. And it's already generating something that actually looks like text. Does it look like Shakespeare? No, it doesn't even look like English. But it's fine. If we continue, you're going to see that all of a sudden starts to actually start with the character, which is quite interesting. And if we continue, this keeps on getting closer and closer to English, to the point that if we go to the end, King Harry VI, in this tongue of company, as the command of her and command of the command, and the consent of his heart to come on him. This could be Shakespeare. I don't know. I do not really understand Shakespeare when I read it either. So it might be Shakespeare. And this is something that literally took 1 hour of training, right? So imagine if you keep training this over and over, because this is actually far from being as much as you can train the Disney network. I trained this morning, right? So you could definitely do more than that. Actually, this was, let me see. So yeah, epoch 5, and the accuracy is still 60%. We can go much higher than that without any problem. Cool, so that's kind of nice, right? But we're talking about source code. So what happens if the input, instead of being Shakespeare, is Go code? So it's actually surprisingly good. No, don't do this to me. Okay, so the problem now is that Chrome is trying to re-render a lot of output. So it's gonna take some time. There you go. Okay, so what I did is I cloned the Go repository. I got all the Go files from it, and I started training it. Same thing, there's way more files. And we start training it, and actually I'm gonna run them. Okay, so we start with this, which is pretty bad. I think we can all agree. Generating random. Okay. This starts to look, it understood that indentation is a thing. It doesn't really know how to use it yet, but it's a thing. Now it starts to look a little bit more, but like parentheses are not paired. Same for brackets. It is pretty bad, but keeps on learning, and actually quite fast. I think it was here. How many of you have written Go code before? Okay, so it appears a lot in the training, but also quite fast. It starts to figure out that that's actually totally a thing, and you should write it very often, which is kind of cool. This is the same demo. We run it with a lot of Python code, with all of the code from TensorFlow, and after training it for a long time, this trained only for a little bit. By the way, this Google Colab, which allows you to run things for free with GPUs, which is really cool. But yeah, after training it for a decent amount of time, we were able to generate things that look like TensorFlow source code, to the point that it always started with the Apache v2 license, which is kind of nice. Okay, so let's continue. Okay, so this is cool, but is this useful at all? Like, can we do anything interesting with this, right? The important thing to know is that when you're predicting something successfully, you actually understand it quite well, right? And not only that, but you're also able to predict and to detect when something is weird, an anomaly, right? So what we did was we got all of the identifiers that we could find on public Git archive, which is lots of them, and we used, basically it's like, oh, if it's Go, it's going to be camel case, if it's Python, it's going to be serpent case, and we used that to split all of the identifiers that were obviously splittable, right? Then we trained a neural network, recurrent neural network, on the bytes of all of those. And we're able to, let me see, create this model that if you imported, now is the Wi-Fi gonna, okay, it's working now, cool. So you're able to load the model, split, and given that splitting identifiers for the win, once it loads, because the Wi-Fi is being not very collaborative. Okay, that's loading the model, takes a little bit. Okay, so we're able to predict that that is splitting identifiers for the win as words, and then quite easily, if you want to actually represent that a camel case, it will fix that for you. The cool thing about this is that if you think about that idea of automated code reviews, now we're able to identify when someone actually forgot to press shift in one of the identifiers, right? Which is quite interesting because it's a problem that for other languages, especially dynamic languages, is actually kind of hard. Okay. So, learning from tokens. We can do exactly the same thing, right? Rather than giving character by character, we give word by word. So the problem is that in order to represent those characters, what we're doing is we're doing one-hot encoding, which basically converts a number from 0 to 10 into a vector with 10 positions, right? So if you take into account how many characters we write as humans in text, in English text, I'd say it's hundreds, probably less than 100 to be honest. In computer programs around that too. But how many words we have, there's actually way more. So if you start working with every single vector is going to have 171,000 positions, that's going to be a lot of memory. It's going to be really hard to train. It's going to take a long time. And how many possible identifiers are in a language, in a programming language? Well, it's kind of like programming languages are like German, where you're just adding more words. So it's actually very, very hard to say, but I think this is a pretty good estimate. Way too many. So what we do is we're going to use embeddings. And I'm going to need to go a little bit faster here. But basically with embeddings, we go from, let's say we have 100,000 positions, 100,000 possibilities, so 100,000 dimensions, where every single word is a completely independent vector in a new dimension, to something that has less dimensions. And we say, these are the 3 dimensions I chose, except we don't really choose them. We just say dimensions 0, 1, and 2, right? And then we just give random values. And just by training the neural network, we're actually going to train this matrix. And this matrix is what we call an embedding. The interesting thing is that the result of this embedding carries a lot of meaning. So you can do things like, well, the distance between man and woman that is actually in the direction of gender is the same one as king to queen. Or walking to walked is swimming to swam. This is from word to vec, which is a very well-known word embedding. What we did was, okay, so we have all of the identifiers that we can find on public Git archive, and we split them into words, and we stem them to have less of them. We end up with a vocabulary of 500,000 words, which is a lot of words, but once we train them with 100,000 repos, we end up with something that is kind of cool, and there's a very good blog post explaining all of it. But the interesting thing, if I'm able to run it here, is, come on. Oh, allocating. Okay, I have 5 minutes. If not, I will just fake it and tell you what the results are. It's fine. Okay, 5, 4, 3, 2, 1, timeout. Cool, so basically we're able to train those and not only find the words that are near an identifier. So for instance, the example I had, Chrome died. So the example I had was what are things that are near square root? And it would find things like cosine and sine and other mathematical functions. But also we can do things like foo is to bar as bas is to cooks. And it actually finds these things. Oh, did it work? No, it still didn't work. Even more interesting, we can find things like send is to receive as write is to read. And it's able to find these things out of the identifiers. The future of this is that this is only just one piece of the puzzle. We're going to be learning from trees. In order to learn from trees, what you need to do is first define what trees are. We have universal abstract syntax trees, which is basically a common way of representing abstract syntax trees in every language. And I'm going to go over fast. And we can also do structural embeddings. So basically, the embeddings we had before are from words to vectors. We want to go from trees to vectors. And then those vectors being allowing us to basically say how similar two trees are based on the data sets we train them with, which will allow us, and by the way, there's papers about this. There's two papers that I really like. The structural embedding of syntactic trees for machine comprehension. This is about actually natural language, but it applies really well to what we're trying to do. And also a general path-based representation providing program properties. Super interesting because rather than using the whole tree, it will say for loops. Well, if it returns true, it's very different. It returns an object, right? So it will be able to actually give that more relevance. So it's quite interesting. And the idea is that once we have those structural embeddings plus the embeddings of the identifiers, we'll be able to do much more interesting things. We have things like finding two repositories are similar or not, based only on the source code, not on the documentation. Finding what are the topics of a piece of code or a full repo. So basically trying to predict the GitHub labels. We are able to do that right now. It's pretty easy. And finally, if you're interested in like more papers and stuff like this, we maintain a list. It's called Awesome Machine Learning on Source Code. It's one of those awesome lists. And it keeps on growing. All of the papers that I mentioned are there, so I invite you to go check it out. It's where I end up reading every single time I fly. And I'm out of time, so if you want to know more, feel free to join our Slack channel. So if you go to source.tech, you'll see a very large invite form with your email. You just put your email there. And we don't really have time for questions, but I'll be around. Also, feel free to send me emails or follow me on Twitter. And I'll be giving a talk tomorrow too, so just find me and ask me more questions if you have them. Thank you.